In the very end, we were looking for a current integrating decision feedback equalizer. So let me just go through the current integrating DFE. And the main difference between this and the regular DFE which we have seen is in a regular DFE decision feedback equalizer, the implementation, you have a ISUM current which was equals to GM times V in minus IDFE, the current which is coming through different taps of the feedback taps for the equalization. So this was the current, and this current was going into a load RL ideally. So this current was going to a load RL ideally, but that load was not ideal, and you had a parasitic capacitor, and which was creating a pole at the output. And this pole was limiting the settling of the VSUM node, which you can use to settling of the VSUM node, which is the delta V voltage, which it will generate as an input to the comparator. So here I showed that, let me just write, V in has two components, which is one is V cursor and the other is VISI. And what we try to do is we try to match GM times VSI, ISI is equal to DFE. So this ideally should be equal to 0. And what we got was GM V cursor times RL by 1 plus SCL RL. So the best case is that VSUM max is equals to GM RL V cursor. This is what we have. Then we told that there is no limit, there is no settling limitation on the current part itself, but on the voltage part. So we said that, okay, I will have this ISUM current and I will integrate the ISUM current over a capacitor for a time period, 1 bit period. And now this is the new VSUM node. And to a first order, we say that this gain for 1 bit period is actually higher than the, if I assume that same CL captured is in both the cases, then this voltage is higher than the the settling RLCL counterpart. So let's look at that. This VSUM is equals to 1 by CL into ISUM. So we assume, let's say GMVISI is equals to IDFE. Then you have GMV cursor, that is the only current, dt 0 to t. T is a bit period here. Okay. So now the new VSUM is, now I am making an assumption here, I will go in detail of that. I assume that the V cursor remains constant for 1 bit period. Otherwise, I have to take the time dependency of the V cursor. So if I assume that is constant, you have GMV cursor by CL into bit period T. Okay. Now you consider this VSUM due to integration by VSUM due to settling, RLCL settling, let me call that. This is equals to GM V cursor T by CL. Okay. And the other one is GM V cursor RL into 1 minus e power minus T by RLCL. Did everyone get this? This is just like a first pole settling. And T is the time period which we am looking for. Like for each bit, I will use that. Now this is equals to T by RLCL into 1 minus e power minus T by RLCL. Okay. If RLCL is the time constant, then this is equals to T by tau 1 minus e power minus T by tau. I'm just writing it as a time constant. Tau is equals to RLCL. Okay. So can you say what about the denominator? That what can be the maximum value of the denominator? 1. And if this is the maximum value of the maximum value of the denominator is 1, at that time what is T by tau? Pardon? Infinity is fine, means okay, so you can say T by tau is okay. If you say T by tau is infinity, then as per this equation you see V sum slash integration is basically infinitely times larger than your V sum of settling. Okay, but that is normally you cannot have a T by tau as an infinity. You have a tau as some fixed value, and normally you look for, let's say, 95% settling or 99% settling. So for 95% settling, T is equals to 3 tau. If you go for, I think, something as 99.9% settling, you will have T is equals to 5 tau. So yeah, so this is how the output will change. So let me assume that if T by tau is equals to 3 time constant, where you are getting a 95% roughly settling, so you are having 3 closer to 0.05. So this is, sorry. So no, this is will become in 1 minus e power. So let me say this is closer to 1. So approximately V sum of integration for the same load capacitor is 3 times larger than the V sum of settling. Now what does this lead to in an actual design? You know that I can get a 3 times larger voltage with the integration time. So and the delta requirement is fixed. So if I am getting a delta V as a minimum voltage as an input to the comparator, if I keep that thing fixed in both the cases, what do you think about the power consumption in an integrating type? So my question is this, that delta, let me just say, delta V min is fixed for comparator, right? So now I'm asking about power consumption in RLCL settling type. Pardon? You can look for the energy consumption. Power consumption is also fine. So energy consumption you will just multiply with the time period. So let's just look at a constant power consumption here, because the current is constant. We will look at the implementation and the current is constant in the picture. So power consumption in RLCL settling type with respect to power consumption in integrating type. What it should be, greater, lesser, for same delta V min I want. And you have just seen the expression before that if I keep everything same, the V sum of integration is 3 times larger than the V sum of the settling type. Isn't this straightforward? Huh? No, no, that's what I'm saying. I am not. Why should I keep the same I naught? If the requirement is on the input to the comparator. I want to keep the input to the comparator same, and I have two different topologies, so I can vary the current. Pardon? Which thing kept constant? Yeah, bit period is the same. Yeah, I mean, in a very rough estimate, power consumption in RLCL settling type will be 3 times larger than the power consumption in an integrating type. Okay. In an actual implementation, that might not be the picture, because of some other things which we'll just look at. But this is very good in the sense to pursue this integrating type further, that what are the problems with the integrating type. Okay, so let me just show you the implementation of the integrating type. So no one has asked the question that if I am integrating it, if you just keep on integrating on some capacitor, the voltage will just go and saturate, right? How do we deal with that? Huh? Discharging the capacitor will take some amount of time. So let me just draw it, so I think that will become more clear. So this is I naught, V in, if we do what? No, 1010, that's not, no, that is, you cannot do it. No, encoding, then you are basically adding a overhead to the data. So you are effectively reducing on the data rate. So we are not, means whatever you, right now in this particular thing, whatever you are doing on a raw random data. You are not doing any encoding. Encoding will help you, means I can also say encoding will help you to like reduce ISI. Also, right, but that's part we are not dealing right now. Pardon? Okay, let's see that how do we do it. So whether it's a large pull-up or something else. So this part is going to the comparator, which is clocked. Okay, so I'm just showing for 2 tap here, and you know that the current which is coming out of this whole combination is what is ISUM. I'm not changing that. What I am doing is I am connecting, means now I'm drawing it very explicitly, this capacitor C to both the nodes, but this capacitor will be a part of the capacitor of the parasitics also, CL, and this node is V sum node, differential you can say that. Now if I just keep on integrating the current, if you are having consecutive bits like consecutive ones, then the current integration will have a different output voltage for each one. So look this thing, right? So let's say I am having 1010, right? In this case, what you are saying is if you are having 1010, then alternatively you are charging and discharging. So in the end, you will, in a steady state, you will have plus minus V differential at the output, some V naught value. Whereas if in the same place you are having all ones, then the output at the end of each bit which you will see will be different. And if you are seeing for the same bit, the output at each bit different, that is equivalent to an ISI. That one bit residue is basically getting transferred to the next one. So we cannot just leave it like this. So what shall we do? For each bit, we should start from the same state, right? So how can we, for the each bit, how can we start the V sum node from the same state? Yeah. So it's like at the falling edge of the clock, you say that you discharge or charge to a one fixed potential, right? And that is being done by having, we call this as a reset. This is working at clock speed. This is PMOS, so it's an inversion there. So what you're doing at the falling edge of the clock, you are discharging the charging both the nodes to VDD. So at every bit when it starts creating the voltage difference on the fixed node. Now whether you are having a consecutive ones or you are having an alternative ones or any half-circuit pattern, it will be the same. But what is the drawback of this? Huh? No. Okay, let's say it adds the more capacitance, and that capacitance I can always take into account of a CL capacitance. So there was a discussion that whether the CL should be an external capacitance or there should be an internal capacitance of all the transistor which is connected. And the answer to that is, to an extent, it should be consist of all the internal capacitors of the circuit. The external capacitor which you add is only to control the output swing. So ideally, you want to control the output swing, but you do not want to add a capacitor. That's the ideal thing, but you cannot do it. So you add a minimum amount of capacitor, you can control the swing. Okay. So let's say other than adding the capacitor, what will it do? So let me just try it back. So you're having a clock, right? When the clock is high, at that time you are integrating. So let me just give the data here. Let's say this is V in. Okay. So V in data. This is valid for 1 bit period, and I am integrating the difference for 1 bit period, and let's start that the differential voltage is something kind of this, because differentially to begin with it was 0. So this is V sum node. Okay, and then this is the on phase, this is off phase, and in the reset phase I bring it back to 0. That is how I can deal with it without one bit spilling into the other one. But what did this implementation do here? Whatever I have talked about, I told I am integrating the input voltage for 1 bit period. Okay, but because I cannot integrate enough without resetting it, so I have to reset it. So I need a reset period, and the easiest reset period is putting a clock on putting the PMOS on the top and reset it to VDD. So now can you comment on the integration period? T by 2. So now if the integration period is reduced by T by 2, your output swing get reduced. So initially the gain which you were looking for 3 times, now that has become half. Okay. So this actually, there are other ways that you can have same integration period, but that we will look later. Reduces integration time, which reduces gain. Yeah. Right. Now, if you say the reset period is not half of the time, then you have to generate that small reset. That's a pretty valid thing. So in place of this as a bit period, let's say this is the clock, I can have something this as a clock, right? There's nothing which denies me to do that. But now let me ask you the question. You are doing this at 20 Gbps. 20 Gbps, you are having a 50 picosecond. In 50 picosecond time period, you want to have let's say this as 10 picosecond. Normally you have 25 picosecond, but you want to reduce it, you want to, let's say I'm having 10 picoseconds. So can you realize the difficulty in generating a 10 picosecond narrow pulse? So what you are saying is right, and that is actually being done in a lower speeds, that you can create a small reset period, which is maybe 10% or 20% of the whole bit period. But higher speeds, this will not be feasible. And the other reason is, see, if I want to reset in 10 picoseconds, the same node which I was resetting in, let's say 25 picoseconds, I have to increase the size of this PMOS now, because this has to charge the node up to VDD. And if I increase the size of that, then you will see the increased parasitic capacitance will come into picture. So then the capacitance will hit it. Okay. So This is the mean still you are seeing a gain of 1.5 times. That is still a gain. Okay, but this gain is not anymore 3. Okay. Now the other thing is that in this whole thing I have taken an assumption that my Vn is constant during the bit period. This is an assumption. So let's see if what happens if Vn is not constant. So we have seen that Vsum node, let's say for constant Vn is Gm V cursor times, let me still write it as T, which we can't do as per the logic we have seen before, but T by CL, right? This is what we are seeing. Now, if we sum for a varying input, so this will be GM by CL, V cursor of, let's say, something as T times dt, and T goes to 0 to T. Now, here I am considering, so means this depends on what frequency content it is. So let's say you just take single frequency content, which is, so sorry, you have GM by CL, and this is sine of 2 pi t, and the frequency is 2 times t. That is by 2. If t is the bit period, I am considering the frequency, the maximum frequency, which actually I consider where the maximum energy till which you can have the total energy most of the time. So this is 0 to t, and this is Gm by CL, and you can just say 2 goes off. You have t by pi times cosine of pi t by t integration, this is minus 0 to t. So you have, this will give you 2. So you have Gm. So let me just say here V cursor is equals to 1 amplitude GMT by CL. If V cursor is 1, right? Just normalize it. So let me just write V cursor equals to 1 in this case. So you have GMT by CL into 2 by pi. Okay. So variable V in. So now like just compare V, what did I write? V sum, right? Yeah. V sum for variable V in and V sum for constant V in. Okay. That is basically a factor of 2 by pi. It's right, right? Integration and all. Okay. So you see that the gain at a variable frequency is lesser than 1 because the input was not constant. Okay. So this is just for the integrating, because we have not done this analysis for a variable V in case of your regular RLC or settling type, but there also this thing will appear in picture. But I'm doing this thing for integrating type because the integration I just assumed the V was constant. Okay. So if the this is like it says that the integrating type DFE has a frequency dependent gain. So what can you think can be done to have the same gain over different bits. Huh? So I'm saying here you see, depending on the input, you are having many frequency component. So you're not integrating all the frequencies with the same gain, right? So what can we do to have, because this is surely going to add to the losses or add to the nonlinearity in the system. So what can we do to have the same gain for all the frequencies? So, okay, think about this, that initially I told that the input was constant and I integrated it. The input was some representation of the actual input, which is coming now. And then I said that if the input is vary, then this will have a frequency dependent gain. An actual input is like that. So what can we do to hold the input for one integration period? Yeah, if you sample and hold, you can do that. So the way it is being done is that, let me just say, if this is coming, you put a sample clock here. So this is working at phi, you can say it is working at phi naught, phi bar. So you sample the input which is coming and then you integrate it. Now if the sampling causes any issue, that's more detail. What does the sampling introduces in the system? But this is a typical current integrating DFE which is quite often used and is more power efficient as compared to your RLCL one. Okay. Now, overall DFE which we have seen till now, there are two types. One is like this RL resistive settling type, and the other one is the current integrating type. But it's like, let me just sum up the DFE design parameters. The first one is the input linearity matters in both the cases because you are cancelling something with the current. Because you are cancelling the ISI with a fixed gain block. Okay, so the input linearity is you need to maintain with resistive degeneration or whatever, like burning more power. That's input linearity is a parameter here for DFE design. Okay, the second one we have seen is, we see two things. One is resistive settling. This is RLCL settling. Resistive settling is basically slower than current integrating type. Okay, this is another thing which we have seen, and because now, but the current integrating type has frequency dependent losses. Okay. And the last one is, but none of these techniques is doing anything to the first loop. You're not reducing any timing for the first loop which we are closing, right? First loop is still has to close, means from the comparator to the output, whether you integrate for that bit period or you settle it with RLCL, and the setup time for the comparator, that has been untouched. So we are not gaining anything with these two techniques here. Okay, so closing first tab is most critical. Anything else do you think is something which you see is solved or unsolved with this DFE design? Like when you compare the two. Linearity we took into it. Linearity we said it's a resistive degeneration. We had RLCL settling. Or is there any other way you can think that I can get a better settling? Okay, so let me just, so here one thing you can add up is that if I use some kind of inductive peaking at the output of the summing node in case of RLCL settling, you may be able to increase the bandwidth at that node, right? But then you should always take into account the delay part. So normally inductive peaking actually gives you a better extension in the bandwidth because it extra delays in the path. But in this case, we are very much concerned about the delay. So uh, let me just plot the block diagram for the DFE. So look at what can we do. You have a comparator, just plot, and this is W0, 1 flip-flop, W1, let's put it this way, W2, and this is the whatever you can say V in is coming here. This is just a block diagram. Okay, so this is an minus. And the loop which we are concerned about is this. So if I want to see what additional can I do to the loop, which blocks should I look into? So if I want to see, this is the loop which we have seen. In the loop, there is a comparator and there is a gain block. And I am concerned about the settling of this loop. So which two blocks is most critical as per you? Comparator. Okay. The other block is just a gain block. So what kind of comparator have you seen before? This one is a sample and hold, right? Sorry. It's a CMOS regeneration type cross coupled latch, right? Is that the comparator you have seen? So let me just show you one. So the one type of comparator which is used is so this is one comparator which you use where the input is sampled. So input is V in. Input is sampled in one phase at the nodes, this cross coupled node. So let me call them as VOP and VON. Okay, this is just a very bare comparator. And input is sampled on VOP and VON in the phase when the clock is low, and when the clock goes high, these inputs are allowed to regenerate. There will be a reset switch which I have not put, but the basic functionality. Regenerate means you are having a cross couple inverter, right? So you understand the way how the cross couple inverter works. So let me just show you that too. So let's say you are having a very bare okay. So let's say this is ground and this one is VDD and this node is VOP and this node is VON. Okay. So let me just start. If VOP to begin with, The difference which you are having is point, let's say 6, and VON is equals to 0.4. This is the initial voltage which I put up on these cross coupled nodes. So if now look this one, so let's say this is M1, M2, M3 and M4. Okay. Now if VOP is 0.6 and VON is 0.4, which of the NMOS do you think, M1 and M2, is more active? More active means has a larger current capacity. M2, right? So M2 is stronger than M1. Similarly, because of this voltage, similarly you look at in M3 and M4. In M3 and M4, which one is stronger? M3 is stronger. So if M3 is stronger than M4, then VOP node will go higher than VON, right? And as VOP becomes higher than VON, then M2 will basically bring the VON node more down. So this is a regenerative positive feedback fashion. You put a small voltage difference, and because of the positive feedback, you just regenerate it, and then your 0.6 and 0.4 volt will actually turn out to be 1 and 0. So if you want, you can always get the small signal incremental picture that how does it regenerate. But that's this is just an intuitive thing. Which one gets stronger first, and that is like it gets little strong, and then you add more voltage, gets more strong. Okay. So in a comparator, because you are resolving a very small input, you sample the input in this circuit, and then you allow it to regenerate to become a 1 and 0. Okay, but this is a very bare comparator which you have seen, and normally this comparator has an offset. Okay, and the comparator has an offset. What it means is that I put a voltage, let's say, let me just tell you the problem with the offset. So let's say without offset, if I put VOP is equals to something as, to begin with, 0.55 and VON is 0.45, then after regeneration you will have VOP equals to 1 and VON equals to 0, right? This is without offset. What an offset means is that, let's say M1 has a threshold voltage 100 millivolts, example, 100 millivolts higher than the threshold voltage of M2. So if the left pair is slower, means you can say it needs an extra 100 millivolts to resolve something. So if you have that kind of offset, then for the small difference, you will not be able to make out at the end of the, you will go into even a wrong, even in the wrong side. So offset on means with offset, you should, the delta which you start regenerating with is VOP minus VON minus V offset. The sign will be taken as per this in the end. Okay. So in all, and this offset arises because of the mismatch between the transistors, between the transistors during the layout, during process variation, and other things. So what is normally done is that you cancel the offset. So if you are saying that I am having a 100 millivolt offset for my left pair, then I will deliberately apply a minus 100 millivolts on that to bring it down to 0. Means I will change the input on that. So that that is actually called as cancellation of offset. And you can do it in many different ways. You can basically change the voltage, or you can add an extra capacitor at one node of the comparator in comparison to the second, so that one node becomes slower than the other node depending on the offset. So this is offset cancellation, and you can, let me just point out this one, you can cancel offset with like You can say current sources on both the sides. Current sources both the sides means I can, let me, where this go? So if I have a current source on this side, on each of these side, right? I1 and I2. So mismatching the current source I1 and I2, I can cancel the offset. Okay. The other way to cancel the offset is I can add a capacitor on the two nodes, and I mismatch the capacitors C1 and C2 so that I make one node slower than the other depending on which is having a lesser threshold voltage. So all these things have to be done at the input of the comparator so that you can resolve a very low voltage. Okay. And in doing all that thing, normally I will say more conventionally, you have a preamplifier stage before the comparator. And a preamplifier before the comparator has has many good things. So you say, let's say preamplifier. Okay. So let me ask you this. If there is a 50 millivolt offset at the input of the comparator and the preamplifier has a gain of 10, what is the input offset looking in? 1 by 10. 1 by, so the 50 millivolts you look at here as a 5 millivolt offset, right? So whatever is coming from the V summing node, that V summing node should be greater than the 5 millivolt offset to resolve it in a right manner. So it also reduces the input referred offset when you are comparing the minimum switch, right? So it's basically preamplifier reduces input referred offset when compared with the summing node output. Okay. The second thing which helps us is that I can do all this offset cancellation at the output of the preamplifier. I can add or subtract the current sources. I can add or subtract the current sources. I can change the capacitor things. So preamplifier output, offset cancellation at the output of preamplifier. Okay. Now there is one more thing. So let's just bring that. So in this particular comparator, point out. So you see that this is the clock comparator okay. So let's say this is the clock comparator which we are talking now, right? So in this comparator, you see that there is a switching happening. Okay, means the current or switches at M0 and M bottom are there, and then your all these switches, these two switches, both the switches are basically they are clocked at every bit period. Okay, so what those switches do is like they give a kickback or a kickback current to the previous block, and that is coming because you are having a capacitor. Everywhere there is a capacitor. So there is a capacitor here, there is a capacitor here, there is a capacitor here. So you are having everywhere capacitor. This is not what you are putting deliberately. This is something which is coming on its own. Okay, so whenever a switch opens and closes, you have a charge injection going in different direction, in the direction as where you find a lower impedance or not. So what this does is it actually gives a kickback to the previous node. Now, if this thing was happening directly at the V summing node, then the V summing node voltage will fluctuate or output will fluctuate because of this kickback. So a preamplifier is actually separating your V-summing node from the kickback. And you see the V-summing node is also having all the taps, other taps connected there. So the influence there is more. And it can cause a more, like, let's say you change the voltage and then you injected a current and then it takes a while to settle because that is having a larger time constant, the V-summing node. Okay, so this preamplifier also shield you from preamplifier shields you from the kickback at the summing node. Okay, so regular comparator is made up of like two parts. One is a preamplification part, and another is the decision making part. So both the things are there. Now, okay, so let me ask this question. So in place of this comparator, now I have placed, okay, so let's start with this. Now I have placed a preamplifier and an actual decision making block, okay, which is clocked at phi. What do you think you can do now to reduce the loop delay when it comes at the input of the comparator? So the loop delay which we are still looking is, let me just remove this. So, okay, the loop delay which we are still looking is going through all this if we go through the regular procedure and at the input of the comparator. Because what I am concerned is what am I going to make a decision on? Okay. Huh? Yeah, you can increase the preamplifier. That will increase the gain, but it is not increasing the delay. But it is not reducing the delay. So you can say the concern has now been changed from having a somewhat amount of gain to having a delay has become more concerned. So you are seeing, right? Input node is, let me call as a input node X and output node is Y of this whole loop, right? From the clocking instance to the coming back. So do you think that I can do something to the first tap loop? Huh? Okay, so feed for what do you mean by actual feed forward? So where does the output of W naught should go? See, you are adding the W naught gain before preamplifier. What you are concerned is after preamplifier. So I can connect this node directly to this, right? If I'm concerned about the first step, I can try this. Okay, and this is I think this you can. So when I am connecting to this, do I still need to have this connection? Huh? No, for all other taps, I am still going at the input. If I connect all other taps to the same output of the preamplifier, then again the same loading will happen. So all other taps, I am still making the same V-sum path. But for this particular tap, I will go through the closest path. So let me just draw that and then end. So you have a channel with the termination, then a GM block, and we can change it to current integrating type. That is not a problem. Then you have a preamplifier and a comparator, and this one, let's say this is W naught, and if this is a GM cell, this can connect directly to this. That's a summing node. Here, let me just make it as a summing node. So I can do this here, and for all other taps, I still have W1, which is basically, let me call this as GM. Let me just write it as GMW1, which basically adds up to this node, right? So if I am summing at this node, there will be another set. Surely you will have a resistor and a capacitor, but if all other taps are coming to the second node, right? There is only one tap is connecting to the closest node. And the thought in all this is that the time constant at the V sum 0 node and V sum 1 node, so let me just write it as here, okay. So the time constant at these two nodes should differ, otherwise there is no use. So let me say tau of V sum 0 should be greater than tau of V sum 1. Means the desired is V sum 1, so it should surely be lesser than V sum 0. So we'll go into detail of this in the next class. Let's stop here.